When an LLM API feels slow, the standard advice is, throw more GPUs at it. That advice is often wrong, and the reason is one of the least understood stories in production engineering. The real reason inference got fast over the last 4 years was not new hardware. It was a quiet rewrite of how serving software schedules memory, borrowed almost directly from operating systems research that is decades old. Let's trace it era by era, because each fix exists specifically because the previous one hit a real, documented wall. Era 0. The bottleneck nobody names correctly. Every time the model generates a token, it needs the attention keys and values for every token that came before it. Recomputing those from scratch every step would be unusable at real context lengths, so serving systems cache them. This is the KV cache, and it turns recomputation into a lookup. That cache creates a hard split in how a request runs. Prefill, reading your prompt, processes every prompt token in parallel. Dense matrix math, genuinely compute-bound. Decode, generating each new token one at a time, has to reread the entire growing cache from GPU memory on every single step. According to NVIDIA's own engineering write-ups, that makes decode memory bandwidth bound, not compute bound. The math units mostly sit idle, waiting on memory traffic. One published roofline analysis puts decode at roughly 1 floating point operation per byte moved, far below where compute becomes the limit. And here is the number that makes it concrete. For a 70 billion parameter model at 16-bit precision, generating a single token means streaming roughly 140 gigabytes of weights off GPU memory. Once, per token, per request. That is the mechanical reason a second GPU does not cut your latency in half. You are not compute limited. You are bandwidth limited. Era 1. 2022. Batching hits its ceiling. The first fix was obvious and wrong. Batch requests together, sure. But naive static batching locks a group of requests together for the whole batch, and the batch only finishes when its single slowest sequence finishes. One long response holds a batch of short ones hostage. A paper called Orca from Seoul National University and Friendly AI fixed this at the scheduling level. Iteration-level scheduling plus selective batching. The scheduler operates per model step instead of per request, so a finished sequence leaves the batch and a new one joins, every single step. On GPT-3 scale models, Orca reported a 36.9 times throughput improvement over NVIDIA's faster transformer at the same latency. Anyscale later benchmarked the same idea on Llama 13B on an A100. Static batching sustained about 7 requests per second. Continuous batching? About 165. This technique now goes by 2 names: continuous batching in VLLM's world, in-flight batching in NVIDIA's docs. Different names. Same fix. Same wall. Era 2. 2023. The memory nobody had fixed. Smarter scheduling did not fix a second, separate problem. Memory itself. Before 2023, most serving systems reserved one large contiguous block per request for its whole possible KV cache, size for the worst case, even when the output turned out short. A paper out of UC Berkeley, presented at SOSB, measured exactly how wasteful that was. Existing systems, in the author's own words, waste 60 to 80% of allocated KV cache memory. Their fix, called PagedAttention, is a direct borrow from operating systems. Split each request's cache into small fixed-size pages, managed with a page table, exactly like virtual memory has worked for decades. Allocate pages on demand. Release them the moment they're free. The result, running as the system called VLLM, cut wasted memory to under 4% and reported 14 to 24 times higher throughput than plain Hugging Face transformers. Era 3. Sharing memory across requests. Once memory is pageable, a new trick becomes obvious. What if 2 requests share the exact same prompt prefix? A system called SGLang, from researchers including members of the original VLLM team, built RadixAttention, a tree that automatically detects when requests share a common prefix, a system prompt, a few-shot example, the start of a long conversation, and reuses that portion of the cache instead of recomputing it per request. On structured workloads, SGLang reported up to 6.4 times higher throughput than the state-of-the-art at the time. Era 4. Long prompts collide with live decode. As context windows grew into the hundreds of thousands of tokens, one more collision appeared. A single giant prompt's prefill could stall every other request's decode steps in the same batch. because prefill and decode still compete for the same GPU pass. The fix, described in NVIDIA's TensorRT LLM docs, is chunked prefill. Break the long prompt into pieces and interleave those pieces between ongoing decode steps, like puzzle pieces sliding into gaps. Nobody's decode gets stuck behind somebody else's novel-sized prompt anymore. Now, here is a number worth sitting with. Take Llama 3.1 70B with grouped query attention. 80 layers, 8 kV heads, head dimension 128, 16-bit. Independent calculations put its kV cache cost at roughly 0.31 megabytes per token. At a 128,000 token context, one request's cache costs around 40 gigabytes. Before generating a single output token, 4 concurrent requests at that length need over 160 gigabytes, just for cache, on top of the weights. At long context, the kV cache is not a footnote. It can rival the model itself. And this is why the software rewrite mattered more than the hardware. Reporting from the Information in mid-2026 described OpenAI cutting inference costs for ChatGPT's free tier by more than half through serving software changes alone, reportedly shrinking that traffic's GPU footprint from tens of thousands of GPUs down to a couple hundred. That figure is press reporting, not an engineering paper, so take it as directional. But it matches the shape of every fix in this story. The win was never adding chips. It was stopping the chips already there from sitting idle. Every one of these fixes has the same shape. Decode is memory-bound, so batching keeps the GPU fed. Static batching wasted time on stragglers, so Orca scheduled per iteration. Reserved blocks wasted most of the cache, so PagedAttention paged it like an operating system. Identical prompts recomputed the same cache, so RadixAttention shared it. Giant prefills stalled decode, so chunked prefill interleaved them. None of this was a chip getting faster. It was 4 years of somebody finally applying operating systems 101 to a GPU, one bottleneck at a time. Follow compile for what's under the hood.